Today we're going to talk about what is kinetic energy. Now last time we talked about work is defined as the force that causes something to move a distance of d, and work then is equal to F times d. And we make an illustration of lifting a concrete block of 1 kilogram by a distance of 1 meter. And therefore, the amount of work done in that case would be equal to m times g, which is the force, the gravitational force exerted on the concrete block, times h, which is the height I have lifted the concrete block by. And because it's 1 kilogram times 10 meter per second square times meter, and that's equal to 10 joules. So I've done 10 joules of work by lifting the concrete block from the floor to a height of 1 meter. Now today we're going to try to convert that gravitational potential energy into kinetic energy. And it's very easy to do that. All I need to do is simply to drop the concrete block on the floor. And what you just witnessed is that the concrete block started with in a state of relative no motion to me, to the point that it has a particular acceleration when you hear the bang when it hit the ground. All right? Now it has achieved a certain velocity as it hit the ground, which eventually that velocity come down to 0 in the creation of the sound as well as heat when the concrete block hit the ground. So the question is, what is kinetic energy, and how is it a function of the velocity that is achieved by the concrete block? Again, as I can illustrate here, I may have a aluminum ring here, and I can push it by a certain force so that it would start to rub. It would eventually achieve a certain velocity and a constant velocity as it's rolling on the table. So in a sense, the velocity is actually not very simple. You have the velocity of different parts of these aluminum ring moving at different velocity at different time. So it actually comprises two kinds of kinetic energy. One which is the kinetic energy as this move with a constant velocity, and also the kinetic energy whereby this is rotating. Now today we are not going to look at rotational kinetic energy, but we are only going to look at translational kinetic energy. And we ask the question, what is translational kinetic energy a function of, as a function of velocity? All right? So before we answer that question, let's look at some of the so-called kinetics. The term kinetic corresponds to how things move. So we can say a particle, in this case here could be a car, a Tesla that I drive every day to work, and the car may have a position of x. So this is x equal to 0, and this is at that time a position of x. Now, instead of using the term x, let's call that d, because d represents distance. Now, the car may also be moving with a velocity. So at time t, the velocity is v of t. At time t, the distance of the car from d equals 0 is d of t. And also, we may say it's accelerating at a rate of a of t, a as a function of time. So we would look at the relationship between d, the distance, v, the velocity, and a, the acceleration. All right? So what we have here is that d as a function of the distance is the integration from the time 0 to t of the velocity, and we're using the variable x here, v of x dx. So And also, we have the second relationship, which is v of t, the velocity of the t, velocity of the car at time t, is the integration from 0 to t of the acceleration a of x dx. All right? So let's just assume now my Tesla is accelerating at a of t equal to 0.5 g, which exerts a g-force of half the magnitude of gravity. So if you know that g is equal to 10 meter per second square, so we have a 5 meter per second square sort of acceleration on the Tesla. So if you look at the a of t, a as a function of t is a constant at a function of time is a constant at 5 meter per second square. So if you go further to look at what then is a velocity as a function of time, and I use a green color here, and over time this would be, if you do the integration here, that would be equal to a times t, because a is constant, and therefore t would be, this would be 5 meter per second times t. So this would be the velocity of the car, which increases as time increases, and this is the velocity, in this case here, v of t. Okay? Now, if you look at the distance, and I use the red color here, and so if you look at this v integration from 0 to t of a times t, which is velocity a of x dx, and therefore this integration is equal to 1/2 of a t squared. So what you have is the distances traveled by my Tesla would go up as d of t equal to 1/2 of a t squared. All right, so you have these relationship given a constant acceleration of 5 meter per second square. These relationship a here is again equal to 5. Now, what is next? We're going to derive the relationship, which is